Respected principal, honorary secretary, head of the departments, deans, esteemed guests, distinguished faculty, ladies and gentlemen. Good evening to you all. I am Ajay Kumar Reddy K, Assistant Professor, Department of Mechanical Engineering, one of the coordinator of 1 week faculty development program, and Mr. V. Venkatesh as a co-coordinator of the FDP. On behalf of Annamacharya Institute of Technology and Sciences, I find it a privilege to welcome you all to 1 week faculty development program titled Advanced Biomaterials for Orthopedic and Tissue Engineering Applications. I heartily welcome our Chief Patrons, Dr. C. Gangireddy Garu, the Honorary Secretary, Annamacharya Educational Trust, and patrons, Dr. C. Ramchandra Reddy Garu, Chairman, Annamacharya Educational Trust, Sri C. Ella Reddy Garu, Vice Chairman, Annamacharya Educational Trust, Sri C. Abhishek Reddy Garu, Executive Director, Annamacharya Educational Trust, and the General Chair, Dr. S.M.V. Narayana Garu, Principal, AITS Rajampet, and the convener of the FTB, Dr. A. Hemant Kumar Garu, Professor and Head of the Department of Mechanical Engineering. Let me start this session with a brief introduction about our institute and department. Annamacharya Institute of Technology and Sciences, Rajampet, is an autonomous institution and is affiliated to JNTU Anantapuramu. The institute was started in a year 1998 under the auspices of Annamacharya Educational Trust in picturesque surrounding on a spacious 30-acre campus near Talapaka, the birthplace of Annamacharya, the renowned saint poet in YSR district as well. Now it is called as Annamaya district, Andhra Pradesh state. The institute is well located on Hyderabad Chennai highway. Our honorary secretary, Dr. C. Gangireddy Garu, a man with vision, is the founder of Annamacharya Educational Trust. He was born in the year 1954 to Choppa Narayan Reddy Garu and Choppa Rajamma Garu, a farmer's family in Sidulapalli, very close to Talapaka, the birthplace of Saint Poet Annamacharya. About our Department of Mechanical Engineering was started in the year 1998 with an intake of 60 students and gradually increased to 180. The department is headed by Dr. A. Hemant Kumar Garu, having more than 20 years of experience in academics, and he is being served since long to the department at the various positions. The department has well qualified and experienced faculty members. The department is endowed with well-equipped labs which meet the standards specified by the Jawaharlal Nehru Technological University, Anantapur. In addition, the department maintains its own CAD lab with 4 workstations and is the first college in Rayalaseema region, a CNC trainer, a lathe, and a CNC milling which holds in the laboratory. The department maintains its own library in addition to the Institute Central Library. The department is accredited by NBA thrice. The aim of this FDP is to share knowledge with you about advanced biomaterials for orthopedic and tissue engineering applications. I am pleased to say that all the distinguished speakers for this FDP have already made a mark in the areas of research. One minute, please. Distinguished speakers for this FDP have already made a mark in the areas of research and have their own identity. To share this knowledge to us and to guide us, we have efficient speakers. I would like to express my sincere thanks and greetings to all the speakers who accepted our invitation to deliver the lecture on the topics which are already given as per the schedule. Now, I request our principal and the general chair for this FDP, Dr. S.M. I would like to Now I request our principal and chief patron for the FDP, Dr. S.M.B. Narayana Garu, who is the general jail for this FDP, to deliver his wishes on this event to the participants. Sir, sir, principal sir, please unmute and speak, sir. Principal sir,
Okay. Tell
sir.
me. Hello. Am I audible?
Yes, sir. Yes, sir.
Okay. Okay. Thank you. Thank you, Ajay. Good evening, everybody. I welcome you all to this FDP on advanced biomaterials for orthopedic and tissue engineering applications. First of all, I congratulate the organizers for organizing a latest and an advanced topic like this, advanced biomaterials for orthopedic and tissue engineering applications. If we take the history of this artificial limbs, organs of the body, the latest one which has made a history is the one which Abdul Kalam and Somaraj Garu jointly made a calipers using some polymers which weighs only 1.2 kgs, whereas the calipers which the amputated people and the polio affected children were wearing was 12 kgs, whereas the calipers invented by or manufactured by Abdul Kalam and Somaraj Garu weighs only 1.2 kgs. See, it has reduced the weight, and also it has facilitated so much of convenience for this people in orthopedic side, that is for the polio affected children, so that they are able to wear the calipers and they used to run on the roads. And this has given inspiration for many. and people have started finding materials which are compatible to the human body, so which can be even replaced. The artificial biomaterials which can be replaced with the organs which are foregone by the people, or replace the organs which are not there in the body, that not there in the body for so many reasons. And this is a latest technology. Of course, there has been a history for this, but still it is a latest technology, and there is so much scope for research and innovation and invention also in this field. So for selecting this type of advanced biomaterials for orthopedic and tissue engineering applications will be really useful for the participants, and all the participants I feel are from mechanical engineering and from electronics and communication engineering only. And even if they are not from these backgrounds, they will certainly be from engineering backgrounds only. And for these people, it will be very much useful. And my appeal to all the participants is kindly kindly listen to and try to listen to the speakers who are experts on this subject, and try to implement this so that your contribution to the society will be useful to the society. And I thank once again the organizers and also the participants for participating and organizing this type of FDP. Thank you. Thank you very much. Ajay?
Thank you, sir. Thank you for your
Okay.
valuable wishes and conveying the importance of this particular FDP. Thank you once
Okay.
again, sir. Now,
Okay,
I
thank you.
request our FDP convener, Dr. A. Hemant Kumar Garu, Professor and Head of the Department, Mechanical Engineering, to wish the participants. Hemant, sir.
A hearty welcome. Good evening to you, one and all. My voice is audible? Hello.
Yes, sir. Yes, sir. Audible, sir.
A hearty welcome to all the participants on behalf of Mechanical Engineering Department. I need to say thanks to AICT for providing this opportunity, and I thanks management for giving the support in doing the same. So what I want to say here is this type of FDPs are useful for updating ourselves for the new technologies. Olden days, textbook knowledge is sufficient for us, but we have to update now. So in order to update, it is difficult for us to read textbooks or anything. So that this type of FDPs is useful to update ourselves for the same. So this is a platform utilized by all the participants to update your knowledge. I need to say best wishes for all. Thank you for giving this opportunity for the organizers. Thank you, Ajay.
Thank you very much, sir. Thank you very much for the wishes. Thank you, sir. Before proceeding to the today's session, I would like to request Mr. V. Venkatesh, Assistant Professor, Department of Mechanical Engineering, also the co-coordinator of this FDB, who is instrumental in contacting the speakers for the entire FDP, I would like to ask Mr. V. Venkatesh to give brief introduction about our today's speaker.
Good evening to respected faculty members, my colleagues, as well as my friends. So our first session will be handled by Mr. Rajkumar Ukkuturi. So it's my honor to introduce Mr. Rajkumar Ukkuturi. He's the founder of Pod 3D, a company specializing in sheet metal fabrication and casting patterns, and also serves as the founder and managing director of Mekuva Technologies, which is located in Hyderabad. Mekuva Technologies focus on delivering advanced 3D printing services and innovative products, playing a key role in growing manufacturing technology sector in our country. With a passion for innovation and technological advancements, Rajkumar has been driving force in revolutionizing 3D printing and manufacturing solutions in India. His leadership at Mekuva Technologies showcases his dedication uh, uh, to force innovative and expanding the capabilities of modern manufacturing. With this small introduction, I would like to request Mr. Rajkumar to handle this session. So, Rajkumar sir, I hope you are there in. Hello, Rajkumar sir, I hope you are there.
Yeah.
Rajkumar sir, good
Hello,
evening, sir.
everybody. Yes, I'm here. I'm just waiting for the mic permission to come. Okay. Hello,
Fine for
everybody.
that, sir.
Yep. I hope I'm audible to everyone now. I'm audible to everyone.
You are audible, sir.
Perfect. Okay. So, hello, everybody. Let me share my screen. Just a minute. I think I need a permission to share my screen also. Yes, I got it.
Just a minute, sir. I'm doing it.
Yeah. Just a minute. Please.
Your screen is visible to us, sir.
Okay, perfect. Let me. Just a minute, please. Sorry. Okay, you can see the enter screen, right? Of the presentation.
Yes, sir.
Okay, perfect then. So, hello everybody. I'm Rajkumar, founder and CEO of Mekuva Technologies. So, introducing myself, I started my journey as a tooling engineer after my graduation in 2021, in 2017. After that, I worked there in the tooling industry for more than 1 year. And during that time, I joined CITD as tool design and CAD/CAM course. During that period, I got into like few courses which are related to 3D printing, and I got excited during that time. Like the industry was new and it was like full of possibilities. After that, I chosen my entire life. 3D printing is the go. From 2019 till this day, I am in this industry and I'm going to be in this industry for the next 10-20 years definitely. So Meko is a technology startup. Let me put it in full screen. Everyone can see my screen, right? It's in full screen right now. Hello.
Yes, sir.
Okay, perfect. So Meko is a technology startup, uh, like building industrial grade 3D printers. Just a minute. Yeah. So why we started Meko is frustrated by 3D printers. Like 3D printing, you might already know, like it's not very reliable. Like frustrated with our own problems, we started manufacturing 3D printers, testing with different existing machines and doing some mods. Initially, we were selling mods and also providing services like 3D printing services to other customers. We thought, why don't build our own machines instead of investing on existing machines? Let's say customer want to make a object. Instead of getting the Statue of Liberty, he got the stringing part. these kind of problems are existing with the already existing machine. To solve that, we thought we'll build our own machines. So if you see existing machines, right now the rest of machines are much more reliable. Earlier it was not the case. They were slower, they were not very reliable. But our machines are, and also they're high in cost and not scalable, limited post processing. Also, there is not much documentation there online. Let's say if any problem comes, the person has to do it by himself. There is no tutorials available. So we make like startup building industrial grade 3D printers dedicated to providing customers with reliable 3D printers suitable for printing high performance materials. And like our USB is mainly into customer service. Like once the customer purchases our machine, he's not just purchasing the machine, he's also purchasing the 1 year warranty as well as lifetime support from us, like on the machine, how to operate the machine, how to run the machine, how to like keep it in perfect condition and use it for the extended period of time. All these are covered by us. So that is the USB of our business model. You can see some of the parts printed by us. You can see the lion here. That was a 14 feet lion. You can see the dog for the scaling factor. And we have printed this bike, this Quanta, Grauton Quanta. We printed more than 15 of this all spare parts. These all 3D printed parts made on this bike. So these are our 3D printers. Like we started in 2021. From that one, so far we have customer like we have more than 500 plus customers, active customers, and we have printed more than 30,000 plus 3D printed parts so far. Yeah. So apart from 3D printers, we also provide reliable 3D printing services using several additive manufacturing technologies. We also offer design, prototype to mass manufacturing services. As a turnkey solution, we build our ecosystem. We offer training programs in schools and colleges to support our ecosystem. Like we have more than 500 plus active like happy customers, like majority into product development, defense, automotive, and education institutions, also catering to hobbyists and startups. We sold the more than 90 plus 3D printers all over India, made in India machines. And apart from that, like product development, defense, automotive industries, majority of them from. So let's dive into the main agenda of this workshop. So the main agenda of this workshop is to understand additive manufacturing. I think already majority of the people already know what is additive printing. So we can skip or we will go through this part very light. So it will cover it very fast. Also various technologies, additive manufacturing technologies, that is also will cover slightly since it is not the main topic, and we'll be more focused on the majority applications in the AIM industries, and will mostly mainly focus on the uh, in the industry, that is medical industry will mainly focus on, and also the future impact of additive manufacturing. Yep. So majority of the people they call 3D printing. So 3D printing is nothing but some people call it as rapid prototyping, some people call it as direct manufacturing, some people call it as additive manufacturing. All these terms are nothing but additive manufacturing only. There are different terms for 3D printing which are in together called as additive manufacturing. So we can see some of the objects printed using 3D printers. Some of them are uh, like aesthetically good, some are engineering oriented, some are medical, some are fashionable. These are all made using 3D printing technology. So as we compare a 2D printer versus a 3D printer, like a 3D printer, 2D printer like paper printer, it has two axes. Print head moves left and right and feeds the paper in other direction. Whereas 3D printer has one additional axis that can make three-dimensional object. So as per ASTM, the 3D printing definition is this one: joining two metals layer upon layer. So subtractive manufacturing already everybody knows. So like we'll take a block of steel and cut it. So this all will skip directly. So one main thing we should why should we invest in 3D printing is there is one important thing. Sorry, I forgot to cover this session. Like let's say once the we need to remove the support material. The standard approach to 3D printing is first we will take the CAD model, then we convert the model into STL format or any standard mesh format, and we'll slice the object into the slicing software that makes the machine understandable code that is called G code or CPEG, different file formats that machine understands, and the part gets printed. Once the part gets printed, we'll remove the support material, we'll machine the part, post process the part, or sinter to fill the voids, infiltration process to fill the porosity of the part. So these are the things. Like if we see this graph especially, so if we see this data, we can see 3D printers actually not just used for producing prototypes. They are actually used for producing end use parts. That means the parts which customers are using in their real life, the parts which customers are using to as an end use product. So these kind of applications people are using 3D printers. The growth is in a linear path, and it's growing. Like this is 2020 data, till 2024 the final production has increased by another 10-20%. So that gives a uh, big belief like key 3D printing is going to change whole manufacturing industry. That we're going to cover in the end of the session as a questionnaire. So market size, if you see, the 3D printing industry is growing every day. So the one we need to focus more is on the importance is the final production. The final production tells us like 3D printers are not just used for prototyping; it's also getting used for end-use parts. That means there is a huge potential now that yet to come that we are going to experience in future in 3D printing using additive manufacturing technology or 3D printing, whatever it is called. And why it is also very important for local bodies like India or any other country to adopt this technology as early as possible, because as every one of us know, during the pandemic, like the supply chain was completely broken. A lot of parts were not available. People has to wait months of time to get a particular part. But that is a very tricky situation. Like you cannot, let's say if it is a medical device, the patient is it need to be served to some patients, but due to some critical part not available, we cannot fulfill to the customer, sorry, we cannot repair it or we cannot use it. But if we have a 3D printing technology locally, like we can enable the local market to uh, produce that part locally instead of waiting for a lot of time, and also dependency on the international market is also reduced, like local capabilities will increase. So also 3D printing is the backbone of industry 4.0. Why? Because like currently we can see the logistic market you are seeing, like logistics, like if someone courier a part from Hyderabad to Mumbai, there are a number of ways the part can reach them. Like they can send it through bus, they can send it through aeroplane, they can send it through train. Multiple options are there. But there is a big data is also called big data. All the courier services are using, which what the big data does is it it prioritizes and uh, like systemizes the all the parcel services in such a manner, like at the least amount of uh, resources utilizing, the parcel gets delivered to the customer, such that we can also implement the same thing for industry 4.0, or it will still yet to come. It's still in the beginning stages only. So once all the data gets feed it through the computer, so it will optimize the manufacturing solution. Let's say we are manufacturing a part, so the material has to move from point A to point B. There is a lot of wastages happening, not in the moving part. Also there is a wastage in planning. So all these wastages add up, and they are not environmental friendly. They are they're bad to the environment. But if we utilize 3D printing and also these technologies, we can save a lot of resources. So we'll dive into the applications of 3D printing right now. So we'll cover teaching and training, tooling, aerospace, and our main focus will be on medical. And remaining, like I want to skip remaining one, but since since it is a faculty development program, having the knowledge where people are using in right now in the 3D printing applications in industry will give some better understanding to the faculty. So first one is training and teaching and training. That is the most important one. Many of us know, like some people say a simple picture is worth more than 100 words or thousand of words. A picture word. But in reality, if we watch a video, like to understand a concept or to understand something, if we watch a video or if we listening voice call or audio recording, our brain processes that information differently compared to reading that same information. When we read something, the brain processes and the imagination happens in our brain. So that is the reason when we read something, the understanding of the concept is much higher. The similar manner, the scientist had found out that when a physical object is handed over to the student, the learning process is almost 5 times better than video or audio process. That means we can simply tell our kids to print some couplings or print a heart or print a uh, like a brain with veins, so the student will understand, okay, this is the part, this is the thing. So their imagination is completely different, their understanding is different. So this is how the 3D printing plays a huge role in students, like where they can understand the concept much better by using 3D printed objects. And aerospace and defense, the one best example is key reducing the support material. Since additive manufacturing is a layer upon layer process, it doesn't require support material if you're printing in powder materials like SLS or DMLS process, where we can keep very less support material or completely remove the support material based on the design that we are using. So let's say using a 10 kg part compared to the same static and dynamic loading conditions can be applicable on the part that is having almost 5 times lighter in weight. So every gram we reduce on aerospace, on aerospace, it's a cost saving as well as improving the performance of the aircraft. So that is one great example in aerospace. And in medical industry is using the 3D printing and it's the boost. Like imagine something like 3D printers are capable of producing. Uh, you can print organs. You can use like you can load the material like cells material on a syringe and you start creating your own organs. That is possible, and we are getting into the stage where we are going to see the 3D printed organs in future, like also orthotics. Like for example, in this picture there is a skull. The blue color part, this called chronicle plates. Generally the people use, they don't make using metal parts, titanium. Earlier some people may used to make this chronicle implants in head in titanium or metal, but nowadays no one is using, still people are using, but mostly patients prefer in peak material. Peak is a high performance material. There is a plastic that is having equivalent strength as aluminium. So the patient will not feel that there is a metal part in their head. Like generally we cannot use metal implants in head. Main reason key, it will the patient always feel there is something in their head. But if you use plastics like PEEK, which is a medical grade plastic that is having equal strength as aluminium, the patient will not feel something is in their head. And the PEEK also allows the bone growth to happen much faster. And this example, this is a AI generated image where we can see like the heart is getting built on a 3D printer. That is possible. People are right now, I think the next speaker, Mr. Manish Amin, he's from Abai. They have machinery which can print organs using in their 3D printers using ink material. That is called selling something that he will explain. The next session going to be very good from Mr. Manish from Abai. So next one is fashion industry. Fashion industry is using 3D printing the best. Like ornaments, dresses, you can name it. Multiple objects are getting 3D printed using fashion in the fashion industry. Like Nike recently, they have completely 3D printed. Nike and Adidas, they completely announced like almost 20% of their total making is going to be done using 3D printers. Their newest shoe that is launched recently in Dubai was completely made using 3D printing. Maybe a few parts were using traditional manufacturing, but majority of the production was done using 3D printers. Yeah, you can go through this link to get an idea about the capabilities of it, because you can see the shoe model, like what, no matter how difficult the shape is, like people can make. Like we are in a situation like currently uh, we are moving from a society where standardization is the way to go. In the previous cases like 10-20 years ago, standardization is the way to go. Like there is a one design. That design is going to stay in the market for 10 years straight. No one is going to change the design. But we are moving from standardization to customization. People want tailor-made products. That is uh, that is as per their preferences. So, and new every day new products are coming and going. To keep up this market, we cannot invest on technologies like CNC machining. Or CNC machining we can rely on. We can not rely on injection molding or technologies which take a lot of time to get into the market. Whereas 3D printers, like, it's very simple thing. If you have 1,000 machines, you can make 1,000 parts in a single day, and you can supply it to the market and check how it is going on, and later you can invest on this tooling part. So this is the uh, capability of the 3D printing. So same, Adidas and Nike, they are launching their own brands. So the future of 3D printing in footwear is very straightforward. Like it's also come under medical application. Like they'll ask the person to walk on a treadmill, where it analyzes the foot data of the patient, and it will automatically generate a sole model that is specifically designed for that patient, that person, so he feel less fatigue on feet, even after walking a lot of 10 kilometers, 20 kilometers. So this is one great example of 3D printers getting used, and people are getting benefited in real world. So one more application 3D printing has, one major application is investment casting. Investment casting is nothing but they make the main part in wax model, they dip it in slurry, and that get solidified. After that, they melt out the wax, and then they pour gold or silver, whatever the material, and after that we get the gold or silver part in the end, and after that that will be polished and given to the customer. And movie industry, who knows, like movie industry is the biggest adopter of 3D printing from starting onwards. Some of the best movies are the one which uses less CGI and more props. Like as one director said, like the best movies are the one not just seen, they are also felt. The same manner, the best movies are the one which not just heavily rely on CGI but also uh, rely on reality of the objects. So we can use 3D printers to make these kind of objects. Like Thor hammer, it was completely 3D printed. In Avengers, there are ton of models which are 3D printed. And this mask from Mad Max was 3D. So there is huge potential. And one other best application for 3D printers is key construction. Construction, uh, let's say there is a construction for the poor people. We need to build thousands of homes. Let's say there is a catastrophic event happened, and there is a lot of refugees are there who need shelter on a immediate basis. We can use construction 3D printers. Like let's say construction 3D printer has one great advantage, one great potential, that is key. People has to come up with some materials. In construction 3D printing, the major advancement has to be done from the printhead and software, and the last one is the materials. Like what are the locally available materials are there. They take the materials, add with some binders, they make their own material. That material is super cheap to manufacture, and they can make buildings for poor people or refugees at very affordable cost. Or let's say the humans want to colonize Mars or Moon, so they cannot bring materials from Earth to Moon, so they can rely on 3D printers. They can source the local available materials on Moon, on Mars, and they can mix with some binder materials that will act as a slurry, and they can use that to make 3D printed homes. So very great application in future. Food industry is one of the application 3D printers has. It is not widely popular, but let's say you want to make your own food in different shapes. That is a great opportunity. That will give the let's say children want to eat food which is more aesthetically appealing. Like also you can do one thing. Like you can have a machine which tracks your how many calories you are consuming every day to basis. So that will give you an objection like whether you are eating healthy food or not. That possibility is there with 3D printers. Like you can simply make your own recipe and print it and eat it, and still it will give the data to you, so that you will not your health will be properly managed using by tracking all these calories every day. So these are the few applications different industries are currently using 3D printers. So now we'll dive into the product development process. Let's say you are designing a medical device. So that medical device, or you are designing a car, anything. So first thing is key, like to launch any product into the market, there are 4 stages. One is conceptualization, next one is design, next one is prototyping, last one is commercialization. So conceptualization means you put your idea on a paper, you make CAD models, how it looks, everything. And next one is you design the model as great as possible, and you test it. Like you print the object, or you produce using CNC machines or different technologies, and you test the object. So if everything is good, then it's okay. You launch it to the market. Or if it is not as good as possible, you what you do? You again come to the main thing: conceptualization, design, prototyping. These stages are very repetitive. If you want to launch any product in the market, these steps are very common: conceptualization, design, prototyping, conceptualization, design, prototyping, and commercialization. Once the product is launched, that's done. Same thing. So we will see how 3D printing is helpful in these 4 categories, and how 3D printing is accelerating this process to launch a product into the market. So first one is product design application represent number one application. Like as we see in the first chart, where 3D printers are mainly used for prototyping. That is the number one application. Almost 34% was occupied with 3D printers are getting used in the world war for prototyping. That means people will test their designs whether they are form, fitment, everything is correct or not. Let's say first application, that is conceptualization, and next one prototyping. Let's say you have a design, you want to manufacture it to test whether it's working or not. So you can choose 2 things. Like you can send the design to, let's say if you go with traditional manufacturing, you go to the vendor, you ask him to make the part. So he will take some time to give a quotation, and after that the the manufacturing process starts. It's going to take 1 day, 2 day, or more than that. Sometimes like if you are located in Hyderabad, if you give some order to any vendor, local vendor, many of the times you might hear these kind of words from these vendors, like kar raha hu, karunga, kar raha hu, karunga. These are the 2 words they keep on saying, like I am doing, but it's keep getting delayed. What if you have, what if you use 3D printing technologies instead of going with the traditional manufacturing? Like once it accelerates, like you can design the part in the morning hours, and during the night before you leave your office, you can simply start the print. Start the print. By the next day you come to the office, you have a part ready that you can use it to demonstrate to the customer to get the final approval, or you can test it yourself, and if everything is good, you can go to the next stage, like finalizing the design. So like takes out cost also. Like if you outsource the manufacturing technology to other one, like it's going to cost like a bomb. Like they will charge a lot of money, since it is in the production. Even in the product stage, you have to invest on a lot of money to get it prototype. And sometimes demands of the customers are not met, because it is a, since I mentioned, so it is a repetitive process: conception, design, prototyping. These steps keep on rotating unless you get the product into the final stage. So uh, this process, as fast you complete, the faster you will able to commercialize it. You can able to launch it to the market, whether it's a medical product, whether it's a mechanical product, whether it's a automotive, anything. So these processes are same for every product to be manufactured. So demands of the customers are better met using 3D printing technologies. So this is one great example, great application of 3D printers in product development. Product development, 3D printing accelerates me faster. And next one is conceptualization. First, as I mentioned here, conceptualization is the number one. So you have a design, you will get it printed and see whether the form, fitment, everything is good, and appearance models. You will also get an idea, like after printing the model, you'll get an idea what is the, how the model looks like, also appearance, how it appears to the customers, how it appears in the real world, how it appears in the real world environment, everything you will understand. Form, fitment, you can check whether it's fitting or not. If not fit, you'll make the tolerances, or you redesign it so it better. And functional prototyping, and you can also check, like some people even say, even the CAD programming, generally the parts we design on a computer, right? they can also consider it as a prototype, since we can view the model on the screen on a CAD program. That is also considered as a prototyping, since we can view the model and we can test the model using uh, what you call simulation like ANSYS or SolidWorks, which has inbuilt analysis software. So that is also considered as prototyping method in our CAD system. So functional prototyping testing, whether it's can manufacturable or manufactured in real time or tested in CAD program. So by using 3D printing technology, the product development is reduced by 90%. This is not said by me. It was said by one of the biggest company of 3D printer manufacturers in the world. That is called Stratasys. And prototyping cost falling from 12,000 rupees to 1,400 rupees in specific applications. And tooling is one great example. Like since you are medical industry people, tooling is going to be less important thing, but we'll cover in this one. So uh, tooling is nothing but the definition of tooling is main definition of tooling. People say ki external tools, but that is not the correct definition. Tools means any physical components that are used to enable manufacturing of end-use products or prototypes is called tooling. Any physical component used to enable manufacturing of end-use products is called products or end-use. It's called tool. So you can call a drilling as a tool. You can call a spindle as a tool, depending the application. So that is a correct definition. So in tooling, same thing. Elimination of high initial cost. You don't need to invest on high initial cost per fixtures or jigs. You can simply make it. We can also we can skip that one, and we can go to the injection molding application. Like generally injection molding, once a part get injected into the mold, the part has to be cooled down before. If we take the part before that, the part get some warpage. To avoid that warpage, people just keep the same pressure for some period of time. If we use conventional conformal cooling using 3D printer, if the mold is made using 3D printer, we can drill holes in all directions instead of drilling holes in straight lines. So the cooling is more efficient. So we can check this small video from Dugnal Plastic how they in real world. So we can I'll just skip the video to little bit so you can understand. So we can see, so there are some fixtures which they are using. These are all 3D printed jigs that can be used for drilling holes. So Rutnal Plastics is the biggest producer of medical objects in the world. They make tubes. So this has two materials option. Now we'll dive into the 3D printing applications, especially during the COVID period. But that is the best example, and many of you still aware, like during the 3D during the COVID period, COVID pandemic, first pandemic happened. There were scarce of testing material, like ventilator part. This is the one ventilator part that was completely not in stock. So the people all over the world, these are on the right side. You can see these syringes are the one which doctors put in your nose to get the sample from of your body, to whether you are infected with COVID or not. These are all printed in not in these all products were designed not in months, in days, and they are produced in 1 or 2 days only after the pandemic got hit, because the people were not ready. Like everything was scarce. They were like supply chain was disrupted completely. But 3D printing come as a first stage of savior and help doctors, every one of them. And also one example, this mask. This is a many people during that time was very difficult to wear mask, like since it is not comfortable with their with their mouth, so many people get rashes on their skin. Also it was not good for wearing very extended period of time. What the people do is they scan the face of the person and they made the uh, pressure points distributed all over their face so that it was less painful for the doctor to wear for extended period of time of the mask. And next one is door handles, which were manufactured on spot. You can see this Cuba mask that people use, divers put in their in water. That is used as they just printed one small pot on top of it and used as a uh, oxygen concentrate, oxygen mask. So all this done within days of time. The entire medical industry was in huge pain, like it was in huge pressure with the incoming patients. But 3D printing helped them with this equipment to get it faster. And defense is one great example, where people can use. Let's say you are in the let's say the patient is an army person, he has wounded, and he needs some surgery to be done, and not just surgery, he needs some orthotics to put onto it. We cannot send a part printed in locally and send it there. Like the person, it will be an emergency. So if the army people have a 3D printer, they can have some kind of tools which will release the pressure on the bone so that patient can be brought to the mainland for serving. So we can save a lot of lives by doing this kind of orthotics. So this is one great example. You can see this leg, a fracture was happened to the leg, and this part was printed locally on that spot, and it is printed on a 3D printer. That part was weighed on the patient, and he was brought to the mainland. Till that time, the 3D printed part acted as a uh, pain reliever, so that the patient will not get more severe injuries. So one benefit key like of using 3D printers key, eliminating to keep stock kits. Like let's say if I have a pen drive with thousands of designs, I don't need an inventory room where I will put all the parts in spare. I can put all the design files in one pen drive, and whenever I require the part to be printed, I'll print the part and give it to the customer. So stock free, I'm stock free completely. Also you can have the data of very old designs. Let's say 10-year-old tractor design I have. So the customer came and asked me, my tractor, this part broken, I can simply print a part and give it to the person, so his vehicle will be moving, instead of keeping that 10-20-year-old tractor part in my inventory tool. That is huge save benefit. And stocking out and improving oral lead times, we can ship it in days instead of months, instead of getting it manufacture it again. So all this advantage. We'll see one example. Recently, I found this video. So we can see there are a lot of parts printed before the operation got done. So as you can see, like in this video, so the CT scan data that was taken for the patient, like this was a very difficult and very complex surgery, but the doctor was successfully done the surgery. Main reason key, the doctor was prepared, and 3D printing has played a major uh, help for him so that he can decide which veins to cut and which veins are not to cut, which are very crucial, which will which need to avoid cutting, and also the brain separation, how the separation should happen, like printing these objects in multiple numbers. Like you can see, this was a 3D printed part. It has all the blood vessels, tissues. So the doctor can test on these models instead of directly testing on the patient, on the boys. Like it will simply give a big advantage for the doctor in order to instead of doing something wrong and then like ruining the whole lives of the children. Like this is a one great example. So these are few examples of sorry, printed part. Like you can see the blood veins and different tissues in different colors. So we can distinguish like which is the tumor part or anything happens on some particular organ. The doctors has clear cut view instead of simply removing some other part of the body. So even in bones and in medical implants, as we discussed earlier, like maxilla parts, like tooth, teeth, medical application. One great application right now I'm seeing is key the what you call the sorry, I forgot his name. Tutsi, the Tutsi. Tutsi is the one Tutsi is called dental aligners. These are made using 3D printed. Like they print the dental aligner, uh, the directly entire cast of it, and after that use thermoforming process to lay plastic sheet on top of it, and they get the mold of that one. That Tutsi uses 3D printing technology in a wide range. Like we can see all the medical things made on Tutsi, right? These all tooth aligners. They were made using 3D printers. That is the biggest application 3D printers have in medical application. That I forgot to include in this uh, session. So so there are a couple of barriers. Like apart from a lot of applications, there are a lot of greatness about 3D printing. There are a couple of barriers 3D printer also face. One is key some attitude problems. Let's say some people still don't think 3D printing is in a situation like uh, it can replace the existing techniques. The existing techniques are I will say like cost wise 3D printers are costly. The speed also let's say if you produce a part using conventional manufacturing, it is way faster compared to the one you produce using 3D printers. Cost justifications is the number one thing, and a variety of materials, like you have tons of materials available in the conventional manufacturing. Those are not available in 3D printer. 3D printers, you have limited number of materials available, and ease of operation. Conventional manufacturing machines are easy to operate, whereas 3D printers are a little hard, difficult to manufacture. And whereas quality, let's say if you produce a tube or something using conventional manufacturing method, the quality, everything is much better quality than the one used 3D printers. And intellectual property rights, let's say some people still believe like if I share a file to get it printed, the person may not print one part, he may print two parts and use it for himself. So they think there is a loss of intellectual property by sharing the file with a service bureau or someone. So these are the few barriers additive manufacturing faces to get into the real world applications. And this is the end of the session actually. So we also provide like Meko technology. We also provide 3D printer machinery, 3D printing services, teaching courses, and also sell software. Which, let's say you want to set up a 3D printer lab in your facility, we will have a setup like list of machinery which will enable you to have entire setup at very marginal cost, and that entire setup will be connected to the internet and also to the local LAN connection, so you can operate all the machines using LAN instead of roaming around printers. And we will give you the best tools, post processing methods, so that you can start with. That is also one service we provide. So thank you everyone. If you have any questions, you can simply write in the comments, sorry, message section. So I'm more than happy to answer you everyone. Yeah.
Thank you very much for your wonderful presentation, sir.
Thank you. Thank you, sir.
Respected
Yes, sir.
participants, respected participants, if you have any doubts, you can make use of chat box to raise your questions.
Like not just a medical application, you can you ask from industry oriented also. I'm more than willing to help you and give answers.
Our speaker, Rajkumar sir, have extensive knowledge in sheet metal fabrication, pattern
Yes.
making, casting, and as we know, in 3D printing technologies. If you have any doubts in connection to that, we can raise it in the chat box.
Okay, we got few questions. First question is, what are the difficulties you have faced during printing process? So in 3D printing process, if we particularly use FDM printers because we are the manufacturer of the machines. So we particularly face problems ki like metal get moisturized. That is the first thing. Like generally people applications we consider mechanical applications or like may know Mr. Dr. Danila Malik, like whether the application is into medical or mechanical applications or it's medical application particularly. I'd like to ask that question. Medical, okay, got it. So medical application wise, SLA printers we widely use. Like we go customers using formless materials. Like majority of them mostly get printed with ABS resin. That gets the job done in our MacForms P600 machine. The major problem we see in 3D printing is ki moisture. Moisture means the resin material. It get moisture in the air, like it absorbs the moisture from the air, and the quality gets very badly degraded. So that is a major thing we've seen when printing medical parts. Yep. Also support material, like some people, some of the medical application, they want materials like silicon. Like one particular customer, we got almost 1 year ago. He approached us. He has some application where he wanted a part that is completely hollow inside, and it has to be rubbery material, and the surface finish has to be very good. So we tried multiple methods, and final we get into one technique called dipping method. So in that one we make the mold, and that is the most difficult part that I cannot share it here due to the NDA I signed with him. So we'll go to the next question. That is, what is the additive manufacturing not yet commercially used much? Okay, so a main reason ki cost application. Like let's say 3D printers are not something like let's say if you have a conventional machine, the rate of production using injection molding machine. Let's say there is a medical object like what we call, there is a mask. We need to produce mask in bulk quantity. So in injection molding, you can get every 15 seconds you will produce one piece in injection mold. The same production rate cannot be achieved using 3D printing, and also 3D printed parts are weaker in. Let's say if you have a part directly made in using injection molding, that part strength you cannot compare with 3D printed part. The 3D printed part will have almost 4 times weaker than the injection molded part in specific technologies, particularly. And also cost wise, 3D printed parts are much costlier. That is the uh, biggest would say barrier which is stopping people from using it in large scale. Ceramics are used in bone and other human parts in 3D. Ceramics are used in bone, human parts in body. This application I am not the correct one to answer. Maybe next speaker, Mr. Manish Amin, he'll be more capable person than me to answer that question. Ceramics, whether they are used in bone or not. Yeah. Which material is used more suitable for bone implants, sir? Okay. In general, if it is a head part, like let's say if it is a chronical implant, people use PEEK material or material which are very light in light. Let's say PEEK is one good example, as I mentioned earlier. Like it is so the patient will not feel there is something in their head. Like we cannot implant metal part directly on the head area. Patient will always feel something is there. So that is the reason lightweight materials like PEEK they are used mostly. And
So I'm
going,
sorry to disturb you, sir. Can I answer to this question?
yes, sir, please, yes,
One particular participant
yeah,
raised a question: Can
mm,
ceramics can be used in 3D printing
correct.
applications for bone tissue engineering? Yes, there are so many varieties of calcium silicates which can be synthesized by using with the different chemicals, or else natural from natural resources we can extract the same calcium silicate materials, and the same material can be directly used into the human body, or else to improve the other properties which is not possible to handle by the natural materials. By incorporating these materials with polymer and 3D printing technology, we can take that advantage.
Perfect. Are you in material synthesis? No. How are you dealing with that's okay. Which material is more used in additive manufacturing? Uh, like we cannot say like different applications has different type of materials people use. If it is for us, we mostly deal with FDM and SLA. So the number of parts we print on a daily basis, we serve majorly into automotive industry and design institutions. Like let's say some design companies, they are the biggest customers for us, and also automotive industry. And we have one customer who is into medical. Still, they use SLA parts since it has better accuracy, and also generally FDM parts give some kind of finishing that is not very good. That will have some benefit as well as some bad thing. That is key. It will activate the if the surface is not smooth, it will help the bacteria to grow faster. That is a bad thing that you cannot use on a patient. So FDM parts cannot be directly used on a patient. Uh, like you can use sterilization. Like if you have to use in nylon material, you can have to print the part in nylon material so that you can sterilize it and use it onto the patient. Otherwise, FDM 3D printed parts are cannot be used on a patient since it can generate bacteria in a very fast period of time since it has a layer lines. You can use SLA technology for that application used in additive manufacturing. Very is a ceramic and polymer composites. Metal manufacturing based on technology is costly. Developed countries are already using metal AM. Yeah, that's a very valid question. Like metal 3D printers, if you see countries like USA or Europe or even China is heavily investing on metal 3D printers. That is not the case with India. In India, majority of the companies are not the. We are majorly Indians. Indian companies are service-based companies, so they mostly focus on manufacturing capabilities. So what the other countries are doing key since they are designing the parts, so they produce their part, they try to optimize the design in such a manner like those parts can be manufacturable. Like there is a in FDM 3D printing or SLA 3D printing, there is not much focus on design for manufacturing. But if you are printing some parts using metal 3D printing, there is a huge you need to follow design rules like design for additive manufacturing for metal 3D printed part. Otherwise, whatever the part you are going to make, it's gonna have some problems. You need to add support material. This kind of problems will have. This question, I'm also not much. I don't have much idea about the metal 3D printing side since my application mainly deals with polymer type. Maybe maybe in future section some other person who is more capable than me can answer that question. Metal additive manufacturing. That is true. Other countries are heavily investing on metal 3D printers compared to India. That is true. But this question answer has to be given by some other person only. Yeah. You can ask me questions in regarding tooling industry. Tooling is my specialization, CAD CAM, and as well as uh, casting industry. These are the four fields you can ask me questions. I'm more than expert. I'm very expert in in these areas, and you can ask any questions. I will answer. So, any more questions from audience?
Any more questions from the participants?
I think it's okay, sir. Okay.
Sir,
So
thank
I
you very much, sir, Rajkumar sir,
thank you, sir.
for your
Yeah.
valuable information related to 3D
Same, sir.
printing and
I
its
thank Annamacharya
uses.
University, sir, Annamacharya Institute for this opportunity to share my knowledge to the faculty. Yeah.
Thank you very
Thank
much,
you,
sir.
everyone. Yep.
I request to all the participants, please take a 10 minutes break. Then we will have the second session followed up by Dr. Reshma, a senior research assistant from CSIR-NPL, New Delhi. So I request the participants, the eligibility criteria regarding the certificate and criterion for getting the certificate as per the ACT ATAL FDP guidelines. The minimum attendance requirement to be eligible for the certificate is 80%, and there will be an examination at the end, which is of MCQ, multiple choice questions, on the last day of the faculty development this 1 week faculty development program, where 70% of marks is to be scored. Upon that only, the certificate you can download from the ATAL portal straight away after the completion of the FDP. Even you can verify the attendance percentage of this particular FDP from through your login credentials at the portal itself. Please do remember, these are mandatory. These are not in our hands. Everything will be taken care of by the ATAL FDP officials. Please have a break of 10 minutes. Come back. Please join with the one more session. Thank you. Thank you all.
So we request participants do not leave from this meeting. Please stay back in the meeting.
If you can in the keyboard, please press function F5 shortcut.
F5. Okay, okay.
F5.
F5.
Okay, fine. I'm doing. Now, nothing is happening here. I have pressed F5.
Okay.
It's in the.
It's okay,
But
ma'am.
for me,
You can continue your presentation.
Last Venkat sir, if you can see the zoom button plus and minus towards the beside the minus symbol, you can see a slide button. Ma'am, at the bottom of the PPT, you can see zoom plus minus.
zoom.
Beside minus, there is icon. If you can, please click on it.
Wait, sir. On this where we are connected by TMS, you are telling me, you are guiding me on TMS page or on the PPT page?
No, on the PPT, right bottommost corner, you can find a symbol, plus symbol. You can find plus symbol, right, ma'am?
In PPT,
Right bottom.
not in team mode.
In PPT.
Okay. In PPT, I have on the rightmost corner. Yeah.
Ha, ma'am. Rightmost corner. So there is a plus symbol, right? No,
Here it's
right
not
bottommost.
visible.
Right bottommost. Right bottommost.
Right bottom. Okay.
Yes.
Got it.
You can select minus. There is one more symbol, minus. Is there, no?
Okay, fine. I got it.
Next
Now
to
you
that
tell
symbol.
me. Now you tell me. Is this is it okay, or I should maximize it further?
It's okay, ma'am. You please continue your presentation.
Okay. So we were talking about nanohydrogels. So after knowing the problem, the root of the problem, the importance of the problem, now we will move on to the hydrogels which we have aimed to synthesize. And first of all, I would like to give you a brief insight of hydrogels. They are 3D network which are composed of hydrophilic polymer chains, and they are having very much similar porous structure as we have seen in the extracellular matrix of natural bone, with very good biocompatibility, and they are also can be used as a carrier material for cell and bone growth factors. They also facilitate the cell to adhere and differentiate. They enhance the production of bone morphogenetic proteins, which are the markers of osteoblast differentiation. They offer surface area, higher surface area, high surface reactivity, relative strong interfacial bonding, and so on. They have soft texture, so they can reduce the inflammatory response. The mechanical properties is the main issue. The mechanical properties of the hydrogels are not at the power of the bone. So right now we are also thinking in the way so that we can improve its rheological properties, the hydrogel's rheological properties, so that it can be meet to the mechanical properties of the real bone. Apart from it, the hydrogels have superior sensitivity, injectability. We can very well understand that they are easy to inject, and the any shape defect can be filled by the hydrogel. So this is very much very important application of hydrogel. If we talk about if we talk in the tissue engineering applications, injectable hydrogels can also be used as a carrier to deliver biomolecular therapeutic agents. They are able to promote bone mass, bone mineral density, and they are economic also. Processing and cost is very much low. So what is our objective and methodology as a chemist? What we do, we see, we discuss, and we actually recruit the materials which have good biocompatibility, chemically, thermally bioactive, mechanical competence they show. They should have non-toxic site products, which is very important. They should have a good material chemistry, shape and structure, and hydrophilicity ratio should be good. Surface energy, easy availability, we should all consider these factors in mind. So here is a small flow chart kind of hydrogel production. We can use several methods like solution casting, free radical method, irradiation method, physical cross-linking, chemical cross-linking, and it could be done through physical cross-linking. We can do by heating, ionic interaction, hydrogen bonding, freeze thawing. We can do chemical cross-linking by obviously by chemicals, radiations, grafting. So while doing chemical modulation or physical modulation, we should keep in mind that the mechanical properties, the porosity, the physical degradation, it should not be disturbed. It should be at the optimum level. Chemical modulation, we should see the stability at room temperature, obviously, the cell adhesivity, chemical degradation, which is very important factor, that after implanting in the human body, whether it is getting degraded as the newborn is regenerating, the chemical degradation is happening or not, which is very important factor to be discussed. Then biofunctional modulation can be done by covalent immobilization of growth factors. But again, growth factors, we should avoid the use of growth factors if we have to keep the product economic. Okay. So these are different kind of chemical modulations, shift-based action,
Ma'am, we are
mimetic.
unable to see your next two slides, ma'am.
This slide or next slide? Wait.
We can see 10th slide.
Now?
I think, now we can see the other slides. Ma'am.
I discussed this slide.
Okay, but you forgot to change it, ma'am.
Shall I discuss it again?
No problem, ma'am. You please continue. Will you please
So
remote?
now it's, yeah, it is visible now. Now?
But title of the topic is
Wait,
not
wait,
visible,
wait,
ma'am.
wait. Now? Fine?
Huh,
Fine now?
no. Next
Huh.
to that button, one option is there, na, ma'am. Slide share. Next to the negative button.
Yes. Yeah, yeah.
You
Okay.
please click on that button.
Now? Uh, now
Just a
it's
minute,
visible
ma'am.
in the maximize mode or not? I think something. Wait, wait. I'm trying again. First of all, I'm maximizing it and then this mode. Now, is it okay? I have maximized it and I have used that mode also. Is it visible
It's
to
okay,
you
ma'am.
people?
No. You please select negative button. With that, we can able to see entire slide.
Okay, negative. Wait.
Enough, ma'am. Enough.
No? Now I should
No. Now it
slideshow. I should start slideshow or not?
not required, ma'am. You can continue with your presentation. It's not working.
Okay, okay. So these are various chemical modulation methods which involve shift-based action, Michel addition, dialyl cycle addition. Physical cross-linking include the electrostatic interactions, van der Waals force, pi interactions, Hose-Gas interactions, which are basically the chemistry behind the formation of a product. If we are talking about hydrogens particularly, then after choosing and after recruiting our materials, we will go for the characterizations, which include the physicochemical and biological characterization, in which we can take any polymer, which could be synthetic or natural, and making it with the bioceramics, conjugating it with different type of ceramics or bioceramics, and then performing characterizations in vivo and physicochemical like SEMTEM, water holding capacity, XRD, FTIR, degradation, biological studies have also to be done. So these are simple some characterizations which we need to carry out to tell that a product is working or not. So application of hydrogels in bone science and future perspectives, it can treat long bone defects, it can delay fracture healing, cartilage defect can be treated, osteoarthritis can be treated. So nano hydrogels can be seen as a future of bone analogs. If with continued innovation, we can fill the gap between the clinical translation for finding feasible solution for improving patients' healthcare and quality of life. So these are some elements which are very important to play as a role for making a bio or for thinking for a biomaterial for this purpose, like calcium, titanium, manganese, cobalt, and here we can take nitrogen, oxygen means the analogs of these we can consider. So now thinking about composition of bone, because if we are making or manufacturing or thinking of synthesizing a product, we should be familiar. We should know what the composition of bone. We should know. So the 65% in organic matter is hydroxyapatite, which is calcium and inorganic orthophosphates. Then 35% is organic, which composed of collagen protein, non-collagenous protein, and phosphoprotein, osteonectin. These are some of the proteins which include in the 35% of the organic part. So this is the nano reflection of nano advantage of the hydrogels or any biomaterial we are using. So I have discussed it as before. Now this is I told you that our role as a chemist, we have to think of a material which should be biocompatible, chemically bioactive, mechanical competence. It should show non-toxic side products and simple fabrication technique. This is very important. If we will include a complicated technique, complicated method, then it will not be easy to form. It will not be easy to reuse it. So we need to think from that point of view also, that it could be made easily available if the fabrication technique will be simple. So this is the objective and methodology. These are some targeted combinations like chitosan, silk fibrin, and we can take cellulose, we can take polyurethane. These are quite important biocompatible polymers which could be utilized in the biomaterial formation. Then we can design in vivo study in which the histopathological analysis and radiographies can be done, and bone density estimation can be done. So moving on to the application part, that we have to we should make an effort so that whatever we are synthesizing, the biomaterial, that should move to the industry, not just limited to the publication process and getting good quality publication. No, it should come in the market. So we should always work and we should always aim that the material should be enhanced. But yes, of course, it will require many trials, many clinical trials, but at least we can think, at least we can aim from that point of view. So uh, moving on to my case study, which we have done, we prepared a chitosan apatite resin nanoconjugate in the form of hydrogel, and this ternary biocompatible hydrogel has given wonderful results. Whatever parameters I have told you to be count on, that has been given, that has been noticed in the product, and the clinical trials are at present right now. The clinical trials are going on. So components of ternary system: the phenol formaldehyde, resol resin, hydroxyapatite, and chitosan. So this is the possible scheme. The hydrogen bonding can be seen. The calcium hydrogen interaction can be seen. So resol, phenol formaldehyde we took. The highlights of this study was that it was a low cost and effective system consisting of phenolformaldehyde resin, and it was used for the first time with hydroxyapatite and chitosan. It gave excellent in vitro bioactivity, which indicate the possibility to form direct bond with living bone when implanted. If we talk about the osteoblast, the compatibility with the osteoblast, then it shows non-toxic behavior. Mechanical strength was suitable, and the bone regeneration happened in vivo. So we can discuss it further. This is the hydroxyapatite synthesis. So when we will make, this is one of the ingredient, hydroxyapatite. This is calcium phosphate. Okay, so first of all, we prepared this by wet chemical approach. This can be, you can see it, you can find it in many research papers. So this is the wet chemical approach by the reaction of calcium nitrate and DAHP and diammonium hydrogen phosphate at this particular ratio. Stoichiometric ratio should be 1.67. This is very important, okay, to be kept in mind. The pH during the reaction should maintain above 10 because the nucleation of hydroxyapatite occurs at this pH. So we maintain the pH at above 10 with the addition of ammonium hydroxide. And the precipitate we can get, we should neutralize the precipitate and dry it at 80 degrees centigrade. Then further co-precipitation methodology we used for combining resol and chitosan. Chitosan we can find out commercially, chitosan is commercially available. Yeah, degree of deacetylation you can take above 85%. It should be, the DD should be 85%, above 85% for chitosan. Then characterization we did in vitro biological studies for biodegradation, bioactivity, MTT assay, protein absorption tendency, hemocompatibility. Why we are looking at the protein absorption tendency? Because whenever you implant it in the body, the albumin, the protein present in the blood, it tends to absorb, it tends to get absorbed on the implant. So it is important to see the absorption tendency. Then FTIR, XRT, these are primary physicochemical studies which should be done to check whether the product has been formed or not. The same time AFM was conducted, and the mechanical properties, water absorption ability was also analyzed. So these are the in vivo studies which we did, and then radiographical analysis. Now we can move on to the results. So this is the TAM micrographs. Actually, what we did, we formed the 4 analogs of this combination, and with each analog we raise the combination, we raise the concentration of resol resin in each formulation. Okay, so you can see in CHA, and we also compared it with the binary system, which is composed only of chitosan and hydroxyapatite. Okay, so chitosan and hydroxyapatite, here it is termed as CHA. This is the first term of binary system, and these are the ternary systems, ternary system TEM. I think now it's visible. So this is 1 RS means resin with 30%. Here resin is 40%. Here resin is 50%. So in this you can see the agglomeration. The particles are not scattered, they are agglomerated, and agglomeration is not good. It means if we will implant them, they will accumulate into the blood. So they are not, this is not means, as compared to the ternary system, binary system is showing the agglomeration. Then we will moving ahead when we start adding resin into it. Some you can see the scattering, particles scattering, and with increased concentration the particles are getting scattered also, and the needle shaped particles are more visible. Actually in this slide, I think it's not that much visible, but if you will go through this publication, which is in carbohydrate polymers, so you can find out the results more clearly there. Then particle-like, needle-like particles are there with addition of resin. Then if we moving on to the surface morphology, when we analyze it through AFM, then the AFM shows that the surface are getting rough when we are increasing the resin concentration. However, the RMS value in the case of AFM, in case of binary system, the RMS value was significantly low. And RMS value is root mean square value, which reflects the roughness of the surface of the conjugate or whatever material you have taken. So, as much as the RMS value is high or the Z range is high in case of AFM, in case of tissue engineering application, the Z range or the RMS value should be very high. So you can see when we are increasing the concentration in case of resin in the ternary system, the Z range is increasing. The RMS value is going to be 40 or 50 nanometer around. But the binary system is showing significantly low value. So which was the advantage and which was the expected result. So these are the bioactivity studies. Bioactivity studies we did we did on the what we formed simulated body fluid SBF. We form it in the lab. Simulated body fluid, you must be aware that it is the fluid which can be synthesized in the lab, and it is having material elemental composition same as that of blood plasma. So if we want to find out if a material is bioactive or not, we can prepare SPF in the lab, and then we can incubate our material for the particular days. Like I have incubated my material for 4 weeks and 8 weeks, and these are the material surface itself. Means you can see this is the binary system, this is the ternary system. I haven't shown for all the analogs, but this is the best. Means when I increased the resin concentration for 40%, then I got the best result. Not on the 50% also, but on the 40%. I got the best result. So this is the binary system, this is the ternary system surface. You can easily see the surface roughness, how much it is getting increased in case of binary and case of ternary. And if surface roughness is increasing, it means it will enhance the cell differentiation, cell adherence, which are important factors to be included if we are thinking of a material to synthesize. Okay, post 4 weeks, you can see the deposition have occurred on the binary system also, obviously, which is comprised of chitosan and hydroxyapatite only. But if we are thinking, if we compare it with the ternary system, which is after incorporating resin, then we can find out lumps of apatite um, which got collected over the surface, which is easily available, which is easily visible. You can see the difference. And after 8 weeks, this is also showing good apatite formation deposition. But here, if you can see, I can enhance it a little bit. You can see how much intermingled apatite formation have been occurred. These are the wonderful results. Wonderful results. Sam, you can see that clearly the bond, the interfacial interlinking is visible. But in this case, only apatite deposition occurred. But here, apatite deposition is occurring with a very special appearance. Okay, so this was a very much encouraging result after incubating our material post 8 weeks. So you can see the enlarged view here. Post 8 weeks, these are two images which are this is apatite deposition in SPF. Then we performed EDX. You can see in binary system, this is the EDX deposition means calcium phosphate deposition actually we wanted to know. And for our material in which resin was incorporated ternary system, the calcium phosphorus deposition is this. Then some physicochemical characterization. This is the FTIR, in which we can find out the chitosan hydroxyl peaks, the resin peaks, and the apatite peaks here, the phosphate peaks here in this range. So here we performed the TG also, because we wanted to see whether the material is thermally stable or not, and up to how long, up at what temperatures it can bear the means that it can be thermally stable. Because whenever you prepare a material, you have to get it sintered at high temperature. You have to go through the that process in which you will be giving it high temperature to sterile it. Okay, so for that purpose, this problem should also be ruled out, that whether it is thermally stable or not. Okay, so that we perform TG, and we can see that for our material, they are highly thermally stable up to the temperature of 800 degrees centigrade. In XRD, actually what we did, to get more closer look, to get more closer idea of our material, we straight make a comparative analysis with human bone. So you can see this violet spectra is for human bone, and how much our material is resembling with this. This is for human bone, and how much our material is getting resembled with the human bone XRD. So these were very quite you can say encouraging results we found. And this is the SBF study spectra. Actually we incubated for post 4 weeks and 8 weeks, and then we took the XRD. So this is the before SBF study, and this is after SBF study. And here we found the peaks got straightened very much because of the appetite formation. So this is the appetite formation actually happened, which gave this difference. Then moving on to, I think the slides are visible, hopefully. So degradation time we saw, we noticed that when we are changing the pH, how the degradation is happening. So degradation after 4 weeks and 8 weeks, what happened, that degradation and weight loss was significant after 8 weeks. Means with time the degradation is happening. So this should be one of the property of a material, as I told you earlier also, that as soon as the new bone start forming, the old bone or the damaged bone should be degraded. And the material which you have put, it should not be like the new bone is getting formed and the material is also there. No, material should start degrading so that it should get ejected out from the body, and it should get replaced by the new bone. So the material should be like this. Okay, for that purpose, we perform degradation study. This is the compressive stress, compressive strain study modulus. You can see modulus in the range of 1400 megapascal. Similarly, compressive stress was for our material CHA1RS, means with 40% resolve. It was highly in the range of 80 megapascal. Similarly, compressive strength we can see for one means the this material which is having 40% resolve, it is like 120 megapascal. Then we performed the water contact angle assessment also, because hydrophilicity play very important role if we are talking of a biomaterial. So for that purpose, we took the images after a second and after 10 seconds, and we find out that the material is quite hydrophilic. As you can see, the angles for binary system, this is 72, and for after 10 seconds, the ternary system is getting changed to 33.6 degrees. So means the material, the ternary system is more hydrophilic, which is a good perspective to be considered. Then these are in vivo study results. In vivo study results, we actually performed in vivo studies in the albino rat calvarium. This is, you can see, we first of all we dissect, and this is calvaria actually. This is calvaria of albino rat, and we created 8 calvarial defect. You know that for small defects, they can be healed naturally, but the problem arises when it is a critical size defect, means which cannot be healed naturally, or it is taking much time to get healed naturally. So for calvarial defects in albino rat, it is 8 This is 8 limit. So we started the defect. We made the defect with 8 and you can see here 8 defect. Then we fill our material here, and we actually, what we did, I said now that we have to uh, minimize the gap between the lab and industry. So we have to do all the possible, means obviously lab to lab the things are different, the resources are different. So as much as we can do, we should think in that way. So actually, the material which I showed you in the earlier slides, the materials which are commercially available. So they are commercially available. They are used in the industries and they are used in the hospitals. So why don't we compare our material with directly with that material? So for that, ruling out that problem, I took Cerebone. Cerebone is a very famous dental filler. It's a dental bone filler. So I took that Sarah bone. This is the defect which is filled with Sarah bone, and this is the defect filled with our material, and this is the defect which is left empty. For watching, for noticing that whether the defect is getting healed up naturally and in how much time. Okay, then we made a stitch, resolvable stitch, and these are the results. Wait, these are the results. This is this is histopathological results after 8 weeks. So we did 2 types of staining. There are several other stainings which can also be done. So the possible resources, I said that it varied from lab to lab. So we had only these 2 stains. So this is HE staining and this is SR staining. We found that osteoblast formation was there when we filled the gap, the defect with Cerebone. Fine. And there was collagen fiber formation in the SR staining which could be seen. But when we filled our defect with the material we formed in the lab, we find out that after 8 weeks, after 4 weeks, the mediated bone has started, and after 8 weeks, you can see the mature bone has started forming. These are the osteoblasts, this is the fibrous tissue, these are the osteoclasts, and this is the mature bone. Means after 8 weeks, the the bone is getting formed also, and it is getting its strength also. It is getting mature also, which we call lamellar bone. Okay, so after 8 weeks, after putting our material, after 8 weeks, we got the mature bone visible. And in case of commercially available Cerebone, this is Cerebone particles which can be zoomed here. So these particles are present even after 8 weeks. It means that Sarah bone is also working as that our material, but the advantage with our material is that it is getting degraded after 8 weeks, as we have already seen in the biodegradation studies, right? So, but the cerebone drawback with the cerebone is that it is still present at the defected site. So it means it will take more than 8 weeks to get degraded out of the body. So this was the major accomplishment, achievement we can see in case of our study. So These are the picture is more clear here. The mature bone, collagen fiber, osteoclast. You can see this is the main stain which should be seen. In case of HE staining, it is more visible. And here in case of cerebone particles are visible here. Although in case of cerebone, mature bone is also available, also visible, also formed. But I told you that what is the drawback with the commercially available and what is the advantage of using our material. Okay, and then we tested our material effect on the liver and kidney as well. So they have shown normal pathology. So means I told you that they should not uh, eject any side product which could be harmful for the body. Means it is forming the new bone. Okay, it is getting degraded with time. Okay, but will it affect other organs? We should also keep this in mind. If we are testing away any material now, so we should test them on the liver and kidney. These are the major organs to be tested. If you are implanting any foreign material in the body, fine. So after histopathology, we have done the X-rays because micro CT was not available at our institute, and this work was done with the collaboration in AMU Biotechnology Unit and Dental Medical College and Anatomy Department. So this was a comprehensive collaborative work which we did. So these X-ray images, we were happy that we got the opportunity to get the RVGs. These are not simple X-rays. These are the radiovisiographies. So we can, if you can find out, I can show you after maximizing. These are after 4 weeks. 4 weeks. Sham control means there is nothing the left which we have left blank. This is that damaged part. And it's still after 4 weeks, you can see the damage has not been filled. Obviously, naturally, critical size effect cannot be filled. This is CB, Cerebone, commercially available product. You can see after 4 weeks, it is available around the defect. The granules of the Cerebone is can be seen. But here, after 8 weeks, Cerebone was able to make the new bone. But the granules are not visible here in the radiovisiography. But you can see the granules in the histopath. Obviously, which that can give the more clear idea now. So in X-ray, the cerebone particles are not visible, but in histopathology, we confirmed that cerebone was not ejected from the body completely. And this is our material after 4 weeks. The particles are there, but very little. And after 8 weeks, the completely particles got degraded from the body, and the new bone formation took place. These are simple X-rays and these are RVGs, radiovisiography. And these are the explanted tissue. This is sham control, left blank. It got necrosis and it is not getting filled naturally. Then this is cerebone filled with the damage filled with cerebone, and this is the damage, the defected part filled with our material, and it is as if the left part which was untouched. So the results were quite encouraging for us. These are 2 weeks result which I wanted to show you. Actually, if you are getting your woven bone in the damaged part, in the defected part, if you are getting your woven bone visible, it is a very good sign. In our case, we got the results after 2 weeks. We got the appearance of woven bone here. You can see this. This is woven bone. So, in case of this is HE staining, this is SR staining, woven bone should be visible as early as possible. It means your material is quite biocompatible with the body, with the host bone, we should say. So, in our case, after 2 weeks, the woven bone has started occurring, and this is the uh, zoom view, And this is our albino red top and bottom. Bottom, this is the view.
Sir, please stay back. I think madam had lost the signal. Madam will join in a couple of minutes. Sir or madam, please stay back. We are working regarding the technical issue.
Hello.
Yeah, ma'am, audible,
Hello,
ma'am.
ma'am. Can you please share your slides?
Yeah, okay. Wait. Yeah, I was on the last slide. I don't know what happened that it got disconnected. Uh, where I stopped. Have you seen this slide? Conclusion slide?
45th, ma'am.
45th you saw. Okay. I was discussing this gain in bone density. This slide I have discussed with you all.
Yes.
Okay, thank
This was,
you. So, gain in bone density. So, I can continue now.
Yes, madam.
Okay, thanks. So, after doing the histopathology, after doing the radiography, we wanted to quantify this study. So, for that, we performed quantitative gray scale analysis, which is actually the parameter to see how much there is gain in bone density. Okay, so we performed this in the civil engineering department of Aligarh Muslim University. Actually, we could have done micro CT, but that was not available at that time, so we were unable to do that. So, gain in bone density, as you can see, for our material at 4 week, it was 76%. For 8 week, after 8 weeks, it was 92%. The gain in bone density, which was which signified that how much mature bone, how much strengthened bone has been formed. Then this is the treatment group, Sarabone, commercially available group, which shows 42% gain in bone density at 8th week. Sorry, 4th week, and after 8th week it was just 77%. As we can see that after 8 weeks, Sarabone was visible in the histopath slides, right? So I think after 10 weeks or so, it could be degraded completely and it could show 92 or 95% bone formation. And in this group where we left it empty, we did not treat it with anything. Natural healing was visible at 4th week was 18%, and after 8 weeks was 31%. So significant improvement in the gain in bone density was formed in case of our material. So conclusion we can draw that this study, this material was quite bioactive. The osteogenic activities also, the three components which provided the osteogenic activity was improved, and the osseointegration and bone implant contact in vivo was improved. So this composite can be a good alternative material because we are still, the clinical trials are underway. So we hope that this material could play an important role to bring this material from lab to industry. So this is the bionic human. We as a chemist or as a researcher, we can think of the replacements of the several human body parts with our materials, with bone implants. So let's see, and hoping for the best. These are the references, and these are the list of publications. This is the work I have discussed. It is in carbohydrate polymers, so the impact factor has been uh, increased now. So thank you very much. And the presentation is open for the discussion. We can discuss and we can take the questions.
Thank you very much for your wonderful presentation, madam. I request
Yeah.
participants, you can take the advantage of the chat box to raise your questions and get the beautiful answers from the ma'am.
Actually, we can not just questions. We can also give suggestions. If anybody have any suggestions that any other study can be done in this work, because we are on the way to file a patent if we get a good final result. So we are just waiting for that result. Hopefully that result will come in the coming months. So if anybody have any suggestion also apart from the question, then welcome. And if I can help anybody uh, in this kind of research, because we all are here in the field, in the same field, so it would be
Ma'am,
a
we have
good
few
thing.
questions.
Yeah,
Ma'am, we
sure.
have few questions in chat box. The first question is, which SBF you used, ma'am?
Simulated body fluid. This
No, no.
is
He's
no
asking
need.
about which SBF. Okay.
Which SPF means it is only one SPF, which is there in the literature. You can type SBF formation literature. So there are number of papers, including my papers also, which have described the whole material, the whole ingredients which are required. There are several salts which we need in different amounts, and we take buffer, trace buffer, and we form it in the lab at the particular pH. At particular pH means 7.4. So there is only one simulated body fluid which is present. I don't know on the which body fluid you are talking about. I'm talking about the pH which is at 7.4.
And there is a second question, ma'am. Is it possible to make a magnesium oxide for the biomedical implants?
Magnesium oxide.
Yes.
Yeah, yeah. You are talking about magnesium oxide now.
Yes, ma'am.
Yeah. See, magnesium oxide. This is possible, but why don't you think the participant whosoever has questioned this? Why don't you think that we can dope the magnesium into any ceramic? Doping can also be done, na? We can dope it with magnesium. We can dope it with phosphorus. In fact, the black phosphorus is highly in use. So doping can be done to enhance the result, to see the properties. That could be a good option.
Okay. And the other question is, what is the need of thermal analysis in your work?
Yeah, TGA, thermal gravimetric analysis. As I told you, that let me bring that slide back. Um, just a moment. Yeah, this is the slide. Is it visible now? Yeah, so this is the slide, and these are the TGA results. What we do whenever we form a material, okay, we have to check its thermal stability. Whenever there is an implant which has to be implanted in a body, in a human body, or any animal model, or any patient, so we have to get it centered, we have to get it sterilized. And for sterilization there is high temperature required for any material if we are sterilizing. So actually, by TGA, we wanted to see that if we are subjecting it to the high temperature, let's say for 800 degrees centigrade, whether it is getting evaporated or degraded, or its weight loss is happening at a very much significant rate or not. So we found it that it was highly stable, thermally stable up to the temperature going 800 degrees centigrade. So this is the importance, that because of the sterilization process, the material has to be go through the thermal means it has to be subjected to the high temperatures. So we need to get it thermally stabilized, we need to check it, investigate that. Yeah.
Ma'am,
Okay.
myself, Ajay Kumar, the coordinator of the FDP.
Yeah.
I had raised the question why thermal
Yes.
analysis is required in this work. Generally,
Yes.
while doing the bioactivity test, we generally place the maybe a graft or maybe an implant in a SBF solution at 37 degrees centigrade only for
Yeah.
studying the bioactivity.
True, true.
Yeah, but you are mentioning that you have studied about the temperature around 800 or else 600.
Yeah.
Uh, that much temperature is not required
Yeah.
to be tested a material in a human body. I think so, ma'am.
Yes.
That's why I have raised the question.
Yes, true, true, true. Ajay, actually, what is there? See, simulated body fluid is the resemblance of the plasma present means blood plasma. Okay, so it is artificial blood plasma actually, and blood is at the body temperature 37 degrees. So we check our material and we keep it at 37 degree in the SBF, right? That is a different thing. We wanted to see that whether we have implanted it in the body, whether it is getting regenerated or not, whether it is working or not. That is the one thing. Second thing is thermally stability. We are seeing, because we want any material, if we subject it into the body, it has to be sterilized. You know now that even the needles has to be sterilized. If we are doing any surgery, all the equipment should be sterilized, right? So that sterilization process requires high temperature. I'm not saying that it has to be at 800 degree or 600 degree. That we investigated for ourselves, that how much temperature it can bear. But we can go up to 400 also. We can go up to 200 also. It is just for our sake. It is just for our knowledge that how much temperature it can bear. Okay, so it is not like ki body temperature is not 800. Why we are checking it up to that temperature? It is not mandatory, but it is for our sake. We wanted to check our material that how much high temperature it can bear. Okay,
Thank you, ma'am, for clarification.
yeah, yeah,
Ma'am, with your permission, I would like to answer a question raised by Jayavelu. Yes. Uh,
yeah, sure.
the question is it possible to make the MgO magnesium oxide for biomedical implants? Yes, sir. We have some surface modification techniques where we can convert the magnesium into magnesium oxide. Thereby, a ceramic layer will be formed on the magnesium alloy or maybe a pure magnesium, so that it will be interactive with respect to the bone. We have such techniques, especially surface modification techniques. There are few which is possible to coat or else to get an MgO layer on the surface of the implant.
Okay,
That's
that's
the
great.
answer.
Yeah. So which technique you use?
Ma'am, anodization is one process where you can convert material, a normal material to get an oxide layer on the surface. And the other one is plasma electrolytic oxidation. These two are
Oh,
possible, ma'am.
so have you synthesized it in your laboratory?
I'm working on the same area, ma'am. Surface modification
Oh,
of magnesium oxides.
okay, okay. Magnesium oxide particularly.
Yes, yes, ma'am.
Oh,
Especially
great.
magnesium
That's
implants for orthopedic applications.
okay. That's great. Good to know. This
Thank you,
is
thank you,
the
ma'am.
benefit of this discussion. I really want to have other people also to get to participate in such healthy discussions so that we can exchange our ideas, you know, exchange our
Yes, yes,
knowledge.
yes. Yes, ma'am.
Yeah.
Now, one more question from another participant.
Yeah.
How you are preparing the sample for SEM?
For SEM, okay. Actually, what we do, we take a small, in very small quantities needed for SAM, and grid preparation is there. Yeah. So we take silicon grid, and a very small square or rectangle, small grid of silicon wafer is used, and on that a very thin layer is placed, very thin layer of our hydrogel. And if you are taking if you are preparing any composite, means the sample is in powder form, then it can be taken as such. Powder can be scattered on the grid, but the grid will be different then. But here in case of gels, we take silicon wafer as a substrate, and on that we put a very small, we can do the spin coating, or we can do simply spin coating. Yeah, it will be better. So we can form a thin layer and then let it get dry and then get it tested.
Thank you, ma'am. One more question, ma'am, from another participant, Mr. Chitranjan Yadav. How to
Yes,
improve the antibacterial properties on a titanium alloy or metal? How to
titanium
improve?
alloy or metal. Okay, yeah. So,
Antibacterial
like,
properties.
yes, antibacterial. Actually, for this also we have done antibacterial activity, but I haven't shown the results. So, antibacterial activity, for that we can again the silver can be used in combination with titanium, or I think any plant extract. Use some plant extract with that. uh, so it will be beneficial. Plant extract or some uh, we have used trigonella phenum. We have used carbon quantum dots in our latest work. We have used carbon quantum dots that shows very much enhanced antibacterial activity. And carbon quantum dots also we formed from that sand thermal method we used in that method, from the neem leaves. You know, from neem leaves we synthesize carbon quantum dots. So, and then we incorporated it with our metal. I haven't checked with the titanium, but I'm just suggesting that maybe it could give you good results, better results.
Thank you, ma'am. One more question, ma'am. What is the role of tricalcium phosphate in the biomedical implants?
Uh, Tricalcium,
Phosphate, ma'am.
TCP.
Yeah, TCP,
Tricalcium
ma'am.
phosphate. Yeah, actually, the ceramic part, as I told you, that 67% of our bone is inorganic calcium phosphates. So TCP, let it be TCP or SCP or in this HAP, these are all the one or in another way these resemble with the ceramic part. So we actually beta tricalcium phosphate, if we talk about that. So we are actually substituting such kind of ceramics. We are taking them to get it more and more resemble with the natural bone. So it will in our conjugate it will directly contribute to the inorganic component of the bone, in the formation of inorganic component of the bone. So this is the importance of any phosphate, not just TCP, any phosphate if we are taking now. So it means we are actually manufacturing the inorganic component. We have already discussed now the composition of bone. So whosoever is working in this field now, first of all know the bone. What is bone, what is the composition, then you will be having a good idea that what component should be included, what properties should be included, right? So that is why I showed you that slide, that the composition of bone in which most of the part, major part is inorganic, and that is formed by the calcium phosphate, and that could be TCP, that could be HAP, that could be simple calcium phosphates, like that, and so on.
Thank you, ma'am. One more
Yes.
question.
Yes.
Ma'am, for bone implant, thermal analysis is required.
Yeah.
They are questioning, ma'am. Is it required? The thermal analysis is required for a bone implant.
Yeah, we discussed it. No? I think this was the first
Yeah,
question.
ma'am.
Thermal analysis means TGA. So we discussed it in
Yeah, ma'am.
detail. Yeah.
One more question, ma'am. SS or titanium, which one is better?
Sorry, repeat.
Stainless steel or titanium, which one is better for application, ma'am? For
Uh,
implant applications,
See, this is so much documented that titanium is better. But if someone is working on that, as you said, that surface modification is done in your lab. So with some modifications like surface modification or chemical modifications, might be the stainless steel or other materials can give more advanced results. But titanium is, in the market. Titanium is well established material which is used in many hospitals, right? So we can modify other material which we are thinking, uh, any alloy, any other material, so we can modify it and we can compare it with titanium directly. So it could also be one of the research. You can compare the titanium with that of stainless steel and see the characterization part, means physicochemical and other properties. Yeah.
Ma'am, next question, ma'am.
Yeah.
What is the first step in biomaterial tissue interaction? What is the first step
Yeah.
in biomaterial tissue interactions?
Cell will adhere first. Cell will adhere first. Okay. If it is not biocompatible, means if the tissue is damaged, okay, there will be a blood clotting there, right? So first of all, the primary step is the blood or the blood damaged part will interact, right, with the biomaterial. Now it is up to the biomaterial that whether it is causing agglomeration, whether it is causing clotting more, whether it is getting help in the that process, that hemorrhage process and all, and then it get come in contact with host bone, right? So first of all, it has to get means I told you na hemocompatible, and for that we see I don't know whether I've shown here or not, hemolysis we actually first this is very important study. Hemolysis we should perform for our material. So this is the first step, because blood will come directly in contact with our biomaterial, then the host bone, later host bone will come, but first of all blood will come in contact. So it should be hemocompatible, compatibility with the blood. So hemolysis is done, that RBC lysis is happening or not, and how much it is happening. It is happening up to the permissible limit, which is 5%, as approved by FDA. So it is happening in that range, or it is happening in low or high range. So hemolysis should be done first.
There is one more question, madam. If
Yeah.
we take biodegradable material for bone implants, then thermal analysis are required, ma'am. This is the question.
If we take biodegradable materials,
If we take
yeah,
degradable
yeah.
material for bone implant, then thermal
Mm.
analysis are required.
See, it is not like that thermal analysis will be it. Thermal analysis is important parameter to know whether we are taking degradable or degradable or non-degradable material. That is another question. But thermal analysis is important. Okay. Now it comes to the biodegradable material. If you are taking, so you yourself understand that if we are taking too degradable material, means it is getting degraded in minutes. So what is the use of that material? You will implant in the body, it will get degraded in one day or 2 day. So it is not a good product. It should have optimum degradability, and that degradability depends on the problem of the means the where you are implying that material, है ना? So the bone is formed in 15 days or 20 days. So the degradability should be in accordance with that. For small wound, for skin wound, the degradability will be different, right? So for skin wound, the degradability can be low, and maybe it is not required, thermal analysis is not required. But if you are particularly doing bone application, then you have to be careful for thermal analysis. And I am telling you, I am mentioning again and again that 800 degrees centigrade we have tested for ourselves. It is not mandatory to check on such high ranges, but yes, you should check on up to at least 200 degrees centigrade whether your this is working material is working or not, because of the sterilization process, which is very important factor. Before sterilization you cannot put anything in your body. So, and for sterilization purpose the high temperature is required. So at least you can test your temperature, you can test your material up to 200 degree, and not 200, okay fine, to 100 degree, but not below that.
Okay, ma'am. Thank you. And one
Yeah.
more other question is, what is the advanced biomedical, sorry, what is the advanced biomedical material at present for doing research work?
Advanced biomedical materials means you
Yes.
the means the in case of polymers you are asking, in case of inorganic materials you are asking, in which class, because there are various classes which falls in this category.
Okay. Raghunath Reddy sir,
Poly-
ma'am asking that which material, I mean, whether this
Which class
question
you're
is
talking about?
connected to
Yeah, you are asking about polymers or what?
polymers or metals or composites, in which category of material you are expecting a advanced biomaterial.
Raghunath sir, please unmute yourself and speak.
Materials, madam.
Yeah.
Materials.
Materials means
நம்ம அப்படியே போட்டு போயிடும். டூ வீலர்ஸ் இருக்காங்களே டப்புனு உள்ள பூந்து போவோம், அவங்க ஆட்டோக்காரங்களாம்.
அதுவும் இல்லாம இந்த ஜொமாட்டோ ஸ்விக்கி
அவனுக்கு மோசங்க இப்போ.
yes. See, if you are making any material, okay, I'm giving a comprehensive answer. Fine. You find where you want, what do you want from that. Actually, if you're talking about conjugates, they will be of one or two products, right? A combination of one or two products. And if you are talking about natural polymers, see, right now the herbal, the natural polymers are in trend. As much as you can go herbal, means you can use the bark, you can use the leaves from plants, you can use the spices, huh? You can use those makhanas, the present in the kitchen. So you can take the extract the main ingredients, flavonoids and all that which are needed in the bone formation, and then combine them with some inorganic material or some metal, then the combination will be very fruitful. What we are doing in our laboratory, we are going on the natural way, natural ingredients we are collecting. And because what we want to do finally, we want to make a product which should be available to major section of the society, and major section of the society is not rich. They cannot afford high treatment or expensive treatment. So what we have to do, we have to be very economic in our approach, be it the method, be it the ingredient, be it the price value, cost value. We have to be very economic in our approach. Yes, but for the testing of material, we have to be advanced enough. We have to test our material from every aspect so that no finger can be raised on us that you haven't checked that, you haven't checked this. So we have to be careful. We should use very much advanced characterization to test our material. But in approach, in methodology, in ingredients, in procedure, whole procedure should be very economic. So you can try with the natural products. What I'm telling, the metals you can take which are biocompatible with our body, which should not have toxic effects. Okay, and yeah, you can try the hybrid approaches also. You can take the polymers, the not the synthetic one, the natural one. So you can take the extracts, root extracts. There are so many options available. If one want to do really work, PhD work is not that big. Many PhDs can be done based on, if we look around and we find some, many options are there to combine and to make a conjugate. I'm not talking particularly of hydrogels. I'm talking comprehensively for bone tissue engineering applications, biomaterials.
Thank you, madam.
Yeah.
And the other question is titanium implants are biocompatible for all the blood groups.
Yeah, so far they are. So far, there is no report, there is no study which revealed that they are not compatible with a particular blood group. Actually, in dental hospitals where we have collaborated, they use titanium implants only directly on the patients. Titanium implants are available commercially also.
Okay, ma'am. Anyway, thank you very much for for spending your valuable time, and thank you very much for clarifying very different questions raised by the participants, ma'am.
Thank you so much. Thank you all for listening to me and for for my work presentation, for giving me this opportunity to be with you all. And I'm also overwhelmed and feeling thankful to Venkatesh and all the team members, Ajay sir and all. Thank you very much.
Thank you very much, ma'am, for the wonderful session. We have learned something, not something, a major part, like natural, how we can use the natural
Yes,
materials
yes,
majorly. Thank you for
yes.
that, ma'am.
Thank you, thank you. Oh, Venkatesh,
I request the participants, please switch on your video just for a maybe for a while, few seconds. We will take a screenshot of that so that we can able to upload the same to the fatal numbers.
Thank you, Ji. Thank you very much. Yes, Ji. Yes, Ji. Yeah. Yes, Ji. One